with that we move into module 3, and probably this is one of the most critical modules of this course, okay, because this is where we actually take our learnings from the transistor and apply it to build logic gates, okay. So this is, the inverter is actually studied in reasonable detail in this course, because many of these results can then be carried over to the other logic gates as well, that we will see in module 4, okay. So what are the learning objectives of this module, module 3, the inverter? You should be able to explain the functioning of a CMOS inverter, right, which means that if there is a transient input signal going from low to high or high to low, you should be able to tell me how the output signal of the inverter will go. Explain the voltage transfer characteristics of an inverter, which means basically the V out versus V in. When I sweep V in from 0 to VDD, you should be able to tell me what will happen to V out, right? What regions of operation each transistor will go through, what are the points of transition, and so on. You should be able to derive an expression for the trip point of an inverter. This is again a very, very key point that you need to know. Ideally, there should be a very sharp transition when I go from 0 to VDD. Maybe above VDD by 2, you want all signals to be recognized as logic high. Below VDD by 2, you want everything to be recognized as logic low, right? Unfortunately, this, and that's what that trip point signifies. VDD by 2 is that sharp trip point. Unfortunately, in reality, there is also a transition zone where there is an indeterminate region, right, which we will come to. But this trip point is a very key characteristic of this inverter, okay. If it's too close to VDD, then it will take a long time to switch to logic high. If it's too close to ground, then it will take a long time to switch to logic low, and so on. Then you should be able to derive an expression for the delay of an inverter driving a particular load. Then you should be able to derive expressions for static, dynamic, and short circuit power of an inverter. With regard to power, this is the only thing that we will be doing in the entire course. I will tell you what the short circuit power is, what dynamic power and what leakage power are. Same thing will apply to other logic gates, but beyond this we will not deal with power in this particular course, okay. So let's now get going. Logic gate, as we know, right, for example, if I have an inverter driving an AND, right, driving a NOR, and so on. I mean, these gates we are already familiar with, right. So what happens is, each gate, right, as you have seen now, the input, right, to a transistor is basically to the gate, right, which means that you will see some capacitance at that node. In fact, there are capacitances at all nodes. So effectively, this will have some load capacitance, right, plus its own capacitance, right, coming from the drain source and all that. We will look at the origin of these capacitances. But if I now want to propagate a signal like this through this circuit, this signal then has to fall. Then this signal will also fall because the AND is non-inverting, and then this is going to sort of invert, right. All through what you see is a capacitor is either being charged by the previous gate or a capacitor is being discharged by the previous gate. So we will first study in detail these two operations and figure out which transistor has to be used for which operation, and the reasons for why we need to use them in that particular way, right. So we will look at okay. So now let's just look at it very combinatorially. We have two types of transistors, NMOS, PMOS, and we have two types of operations, charge, discharge. So we have to look at all four combinations and figure out which is going to work for what, okay. So let's start with the NMOS transistor, okay. I want to first look at discharging because this we already looked at. What is the direction of current flow in an NMOS transistor? Drain to source. Current flow. Okay, so what do I have here? I have a capacitor which is initially charged to VDD, and then I am going to apply an instantaneous gate voltage to turn on my transistor. With this we already studied, okay, but I am just refreshing your memory in that with that. So if I turn on this transistor, then obviously this capacitor is now going to discharge. Okay. Now here, when we looked at this, right, we were treating these as logic signals. So this is actually 0, VDD, VDD 0, right. So when we propagate a logic signal through some logic gates, we want the logic signal to swing all the way, rail to rail, from 0 to VDD, right. So now, which means that when a capacitor is being discharged by the NMOS transistor, the hope is that it can discharge it all the way to ground, right. So let's see if that will happen here, okay. Of course, for delay purposes, remember we looked at only discharging from VDD to VDD by 2, right. But for logic purposes, I need to take the signal all the way down to 0, right. The delay is characterized by only by that point where the current was in saturation and all that stuff, which is fine. But ultimately, I need to discharge this capacitor all the way to ground. Okay, so let's see if that will happen. So before I now start, tell me which is the drain, which is the source. Top is drain, this is the source. Therefore, what is VGS of this transistor at all times? VDD. After it's turned on, it is at VDD all through, right. Now therefore, this capacitor can obviously discharge all the way to ground, right. Why is that? Because as long as VGS is greater than VT, this transistor will be turned on and it will continue to discharge all the way to ground. Of course, this will also be asymptotic, because after you come out of the saturation region, transistor will enter the linear region, which means now it depends on VDS. So as the capacitor is discharging, VDS keeps coming down, which means the current also will keep coming down, and asymptotically it will come down, right. So it will take some time to go, but eventually it will happen, okay. So this is greater than VT for all times. This is the key thing, okay. Now if I were to use the same NMOS transistor to charge a capacitor, I want to see what happens here, okay. So let's look at charging of a capacitor with an NMOS transistor. What is VC of T now? 0 minus 0. It's been, capacitor has been discharged. Now I am trying to charge this all the way to VDD, right. So therefore, this is VDD. What should I apply on this gate again? Same thing, right. Pulse going from 0 to VDD instantaneously. Now what is the drain? What is the source? Which is higher potential? VDD will always be higher potential, therefore that has to be the drain, this has to be the source. So therefore, VGS of T is what? VDD minus VC of T, right. So what happens is this capacitor keeps charging all the way, and of course current, assume now this is an ideal transistor, it means that there is no leakage current, which means the moment I go below VT, the transistor just cuts off completely and there is no current to charge this any further, So let's assume there's no leakage for now. Okay, this means with ideal transistor implies no leakage. Doesn't mean that this cannot be short channel and all that. I'm just saying ideal means there's no leakage current, right? VGS less than VT means current is 0. Okay, so this, as long as it is greater than VT, it will conduct. So what is the maximum value of capacitor voltage that this can reach? Right, it has to be VDD minus VT. So if I use an NMOS transistor to charge a capacitor, at most I can charge it up to VDD minus VT. Okay. Now of course if there is leakage current, this will continue to charge, but that will charge so slowly that that's not going to be useful for me. It needs to happen quickly. In the on current, it needs to charge the capacitor to VDD for me, right? So this is the maximum value that an NMOS can pass. So this guy is a switch that is trying to pass a high voltage. Unfortunately, it can pass only VDD minus VT, right? Of course, if it is discharging, then it can discharge all the way to ground. The key difference is, in the discharging case, the source was fixed at ground. VGS did not depend on the capacitor voltage. On the other hand, when I am charging the capacitor, VGS is depending on the voltage that is being charged, right? Now this is not just a problem of the, this rail to rail swing, right? It doesn't go to VDD minus VT. I mean, it doesn't go to VDD, it stops at VDD minus VT. Apart from this, look at the gate overdrive also. As this capacitor is charging, VGS minus VT is dropping, which means the current is now, even in that saturation region and all that, my current is actually dropping because it depends on VGS minus VT. So the charging process is also ridiculously slow. So not only is it a logical problem, I don't have rail to rail swing, charging is also extremely slow. Very slow charge. Okay. Any questions here? So identifying the drain and source is the most key thing that you have to do in this analysis. Okay. Similarly, let's now move to the PMOS transistor. Current flows from source to drain. Okay. So now let us look at the same case. I want to look at charging first. So this is going to be connected to VDD. So PMOS transistor, I am going to connect it to a capacitor like this, and Vc of 0 minus is 0. Now what should happen to the input? It should go from VDD to ground. Okay. So first, before we start, as usual, which is a drain, which is a source? VDD is source and this is drain. So which means that VGS of T is what? Minus VDD, which obviously is less than the VT of this transistor. Let me call it VTP. VTP is negative number, right, which is obviously lesser than that, and therefore it will be turned on always. Okay, and therefore this guy can now simply charge up in this particular way using this current. So PMOS charging, no problem, it can go rail to rail all the way to VDD, right? So cap can charge to VDD. What about discharging? Vc of 0 minus is what? VDD, and I am now going to connect this to a PMOS transistor. Of course, this is going to go to ground. Again, what is the source? What is the drain? Top is the source. The capacitor voltage is now the source. This is the drain. So what is VGS of T? No. What is the input? Where has it gone? It's gone from high to low. Gate voltage is what? So it is minus of Vc of T. As long as minus Vc of T is, as long as this VGS of T is less than VTP, this will turn on, this will be on, right? The moment that goes, you are gone. So minus Vc of T should be less than VTP, or if I remove the minus sign from both sides, what should happen to the inequality? It will, yeah. So Vc of T should be greater than mod VTP, okay, because VTP is a negative number, which means that a PMOS can discharge a capacitor only up to mod VTP. So the NMOS cannot cannot charge a capacitor to VDD, it stops at VDD minus VTN. A PMOS cannot discharge a capacitor, it will stop at mod VTP, right? So this implies PMOS can pass only until mod VTP, right? You are trying to pass a logic 0, you cannot pass, you can pass only up to mod VTP. So we will use this later in something known as a pass transistor, okay? Any questions here? Clear? Great. Now, what's the conclusion? We have to discharge with NMOS transistors and we have to charge only with PMOS transistors. Any other combination is just leading to a either no rail to rail swing, and also that will be very slow. Even in the case of PMOS, remember the VGS keeps diminishing with time and therefore it becomes weaker and weaker, and therefore the delay is also going to be ridiculously bad, right? So what can we do with NMOS discharging and PMOS charging? So I am going to construct my first logic gate in this course in the following way, okay? VDD, this is my load capacitor that I want to charge or discharge, okay? Now it turns out that I can just short these two guys and connect the same input to both of them, right? Another important observation, note that an NMOS transistor is an active high switch. In this configuration, when my input goes high to VDD, the switch will turn on and will allow discharging to happen, right? On the other hand, a PMOS is an active low switch, okay? This is active high, this is active low. Okay, because of this natural thing of, I have to put an active high element in the discharge path and an active low element in the charging path, the CMOS gates are always inverting in nature, right? Because when this turns high, the output will discharge. The NMOS turns, the input to the NMOS goes high, the NMOS actually discharges the capacitor, which means if the input goes high, the output will fall, and vice versa. So this is called a CMOS gate, right? And of course, this is an inverter. Why CMOS? It is complementary MOS. You have NMOS and PMOS gates. Okay. So you will see in your tutorial that there are few other combinations which are not robust inverting gates, but they are also inverters in some sense. Clear? Okay. So now let us look at, I apply a signal which is like this, or let me apply an ideal signal for now. Input is going from 0 to VDD instantaneously. Okay. So let us analyze both these cases. So if my input is 0, right, let's assume that the input was 0 for long enough. So which of the two transistors would have been on? PMOS would have been on, and therefore the charging circuit would have been on for long enough, and therefore the output should be exactly. So this will be VDD. Okay. Now I am turning on the input and switching it from 0 to VDD. So what happens to the PMOS transistor? Off, right? What happens to the NMOS transistor? Turns on, and therefore it will now discharge it through that equivalent RC model that we discussed, right? So there is going to be some sort of a delay here, and it will come down like this. Okay, this axis is, by the way, time. This is VDD 0, 0 and VDD. Right? Now exactly the opposite will happen if now the input happens to fall again here, right? This will now rise up further. Let me just draw it more accurately, right? And then at this point, this will again rise with some delay, right? Clearly, when the input is 0, the output is VDD. When the input is VDD, the output is 0, and therefore this is very naturally a CMOS inverter, right? In fact, all CMOS gates are naturally inverting gates. So you don't think of AND OR gates, you think of NAND NOR kind of logic in CMOS gates. Okay.